Welcome back to the classroom. This is Mr. Wong speaking here. We're going to go through another HSC physics type of exam problem. This is from the additional sample paper, question 19 for module 5, which is on advanced mechanics. So this focus is more on motion in gravitational fields, which is inquiry question 3. Let's have a read of the question. A student used the following scale diagram to investigate the orbital properties. The diagram shows a planet and two of its moons, V and W. The distances between each of the moons and the planet are to scale, while the sizes of the objects are not. So here we go. You can see there's our planet there. We have moon V and we have moon W. Okay. We have a table down below here. It says complete the table to compare the orbital properties of moon V and moon W. Show relevant calculations in the space below the table. So we have a quantitative comparison, descriptive words, and qualitative comparison, quantitative calculations and qualitative descriptions. So we can go through the qualitative, or let's go through the quantitative first in terms of the orbital radius, period, and orbital velocity. So when it comes to the orbital radius, as you can see here, the orbital radius of moon W relative to moon V. So what we can see is if we look at the entire add up on this scale, the center of the planet to moon W is about 10 centimeters. Okay, so if we break this down into a ratio, it's a 1:2 ratio in terms of the radius or if we're looking at the distance from planet to moon, and from the moon from the planet to moon W, there's that difference there. So if this is a ratio of 1/3, this is complete whole. Okay, so what we can say is moon W's orbital radius is at least 3 times as large as the orbital radius of moon V. Okay, so let's just try and put that down as a quantitative comparison. So we have, moon W's radius over moon V's radius is 10⁻³ so roughly 3 times larger. So qualitatively speaking, we can say that the radius of orbit for W is 3 times larger than V. So that's what we can do here. Okay, the next one we're looking at is orbital period. So we need to look at some equations that can help define this relationship. Okay, so for the orbital period, we can actually use Kepler's third law. So Kepler's, other way around, number 3, that's r³ over t² over, or equals to, r³ over t². Remember, this is the orbital constant. We are going to name this r here W, this r here V, and this V here, this W. It doesn't really matter which one you use, but as we say, it wouldn't really matter which side you use. Now what I want to do is rearrange the r's, or the radius, to be on one side and the orbital period to be on the other. So with a bit of rearrangement, TW² is here, T v square is here, and r3w rv cubed is here. Now we actually know what the value of this ratio is here. That actually comes from this equation that we established here. So we know that the radius is 10 centimeters for w, and it's 3.3 cubed for the radius of v. So that gives us a value of roughly 27.8 approximate. So it's around that margin, but it's not exactly that. Okay, so knowing that, TW square over V square is equal to 27.8, okay, if we square root both sides, we'll know the differences of the equation. So might just draw the root here. And that actually gives us a value of approximately 5.28. So that's how much bigger the orbital period of W is relative to V. So the orbital period of W is 5.28 times larger than V. Or in this case, technically speaking, we actually would say longer. Okay, so that's how you do that. Now, a quick digression between the sort of round-offs that I've used. You can actually see in this question here, they use 2 sig figs, or what you would like to say 1 decimal place. So if you would want, you might even want to put this in 1 decimal place instead, and you can change it to 5.3. That will be the technical way of going about it to be consistent with the question. So you might want to do that. Okay, so the next one we move on to is orbital velocity. So we're again trying to compare the velocity between W to V. Now there are 2 formulas you can look into. There is V equals to 2 pi r over t, or V equals to the square root of gm over r. Okay, so that's what we have here. Now, we're not going to be using this equation here. The reason being is we need to know the radius and the period of W and V. Now, we do know the radius that was given to us originally in this question, but we don't actually know what the value for t is. We only have a ratio value. We don't have the exact values of the two. So we're going to use this equation here to kind of establish everything. We also know that g is the gravitational constant, so 6.67 10 to the minus 11. We also know that the mass of this planet is also constant. So we actually have 2 constants in this equation. So to simplify, because we're only trying to find a ratio value, we're not trying to find the exact value, we can actually make GMM, let's just assume these 2 is arbitrarily equal to 1, okay? And then we actually use the value of R to help us do the rest of the calculation. So if we do the comparison, so the velocity of W divided by the velocity of V, we get square root of 1 over the radius of W, which is 10. And it doesn't even matter if we make it into meters or kilometers, because we are really here just trying to show a ratio. And then for V, it's 1 over 1, or 3.3. Okay, so plug that into my calculator. If we do this, then to 2 sig figs, it's roughly 0.57. So the velocity of W is 0.57 of V, which actually means it's slower, okay? So the conclusion we can write for the qualitative comparison is the orbital velocity of W is 0.57 times slower than V. So there's our conclusion there. In terms of orbital radius, W is 3 times larger than V. In terms of the orbital period, W is 5.3 times longer than V. And in terms of the orbital velocity, it is 0.7 times slower than V. Or so to speak, it's 0.7 the speed of V. Okay? Might just change that. So 0.7 times the velocity of V, hence slower. Okay, and that's how you do the response to this little table here. Let's zoom out. And as we zoom out, I just welcome you again for watching through this video. If you found it useful, hit the like and subscribe. Take care.